Hello, and welcome to the session. This is Control DERs at Scale using AWS IoT. I am Fabio, a solution architect here at AWS Energy and Utilities. Today, we're going to be discussing on what a DER is, why it's important for utilities, how AWS can help, and finally, I'm going to show you a small demo on how can you use AWS services to integrate and control DERs at scale. So what a DER is? A DER is a distributed energy resource. It can be either small generation, so small solar panels, small wind farms, can be storage, such as batteries or even EVs, or can be a controllable load, typically behind the meter type of assets, which we all have in our homes, such as boilers, pumps, and HVACs. So commissions around the world have tried to create a definition for DERs. If we have a look in the US for the FERC, in the European Commission, or the Energy Commission of Australia, we are pretty much seeing the same definition. There are slight difference, but we are still talking about device which sits on the distribution grid, and it's either behind or in front of the meter, and generally speaking either store, generate, or is able to control some load. But why DERs are important? So if we have a look at an energy profile, so the way we consume energy, we probably are looking at a graph which looks like this, where we have a peak by the end of the day, where everybody is coming back home and starts his appliance, start having showers, starts boilers, and if we look at the future with when EVs are going to, being adopted even more, this is going to have this peak that we have in the evening is going to become steeper and steeper. Now, this doesn't really match with the renewable generation. In fact, the renewable generation is intermittent and have peaks during the mid of the day when the sun is shining as much as possible. So how do we deal with this? Utilities are challenged to match demand and supply all day, every day. But when it comes to the evening, how they can deal with this? First of all, the peak needs to be matched by the size of the transformers, or generally speaking, by the grid. So steeper and steeper peaks implies even more strong modernization of the grid themselves, which is expensive. So utilities really want to delay this expense and try to modernize in a smoother way. So one strategy that has been used so far is demand response, where the peak is shaved slightly by reducing the consumption of selected devices or industrial equipment. So we shut down actually consumption, right, to try to reduce the peak. And this is already something that requires DER control. So you are controlling devices, shutting them down. But DERs are much more powerful. When we talk about EVs, boilers, we can actually try to consume the energy, and battery of course, try to consume the energy when it's created. So we can do something like this, where we try to consume the energy when the maximum amount of generation is in place. So when renewables are their peak. What we can use the energy for, it depends on the DER. We can store the energy as heat and pre-boiling the water, preheating the water. We can pre-charge available EVs that are already attached to the grid. And when the peak comes, it will not hit as hard because I come back home, my boiler is already hot, so I don't need to turn it on. And also, when it comes to EVs, we can also control the charging of when I plug my car. It doesn't consume as much energy immediately, but I can plan the charge over the night, so the peak doesn't hit as hard. This really helps also to decarbonize the grid, because those peaks are usually matched using peaker plants, which are carbon emitting. In this case, since the peak is no longer there, those carbon emitting peaker plants are not even required, so they are not used, and no more investment are going to be used to create more. So which are the challenges to integrate and leverage these DERs? First of all, we are thinking about a number of devices which is by the millions. We are speaking about boilers, AVs, and devices which are really, generally speaking, behind the meter. So we are addressing an enormous amount of data, an enormous amount of devices. So we need a platform and a solution which is able to scale seamlessly. Second, then, their status is opaque. It's not clear what the status of the ER is. They're distributed, they're everywhere. We are not directly in control of them. So it's required to have a strategy to control their status at all time. And about connectivity, that's also another issue because we don't control them. We don't provide the connectivity to those devices. They can disconnect anytime. So we need to make sure to have a solution as well to be able to reliably communicate with those devices. So how AWS can help? AWS has a suite, a full suite of services which are designed to connect and control devices at scale. AWS IoT Greengrass specifically is a runtime which is designed to extend the AWS cloud to the edge. AWS IoT Greengrass provides the capabilities to reliably deploy software at the edge with the custom logic that you decide. AWS also provides a number of components already available for you to deploy at the edge. AWS IoT Greengrass also enable you to directly connect with these already available components to AWS IoT services back in the AWS cloud. So you can use AWS IoT Greengrass to extend the cloud and deploy the code and those components into DERs or into gateways. So if the DER, you are a manufacturer, for example, you are thinking to enable your DER to be smart and connect directly to AWS IoT, you can run AWS IoT Greengrass directly on your DER. AWS IoT Greengrass doesn't require many resources to run. It can easily run on a Raspberry Pi. Another option is, if you already have a DER and you want to integrate it in your solution, you can have a gateway, which is a small gateway, as we mentioned, our Raspberry Pi works fine, to run AWS IoT Greengrass to connect with specific protocols to the DER, and you can read that and control it and report this functionality and data back to the AWS IoT cloud. So AWS IoT Greengrass has been designed specifically to help customers to innovate faster and focus on their core business. If you use AWS IoT Greengrass, you can avoid just having your own custom solution, and you can go faster to the market. Thanks also to AWS IoT Greengrass features such as the release of the software, which is managed by AWS IoT Greengrass, the security features, and other features that we're going to see in a few slides, you can save a lot of time for the go-to-market and a lot of CapEx money. But also, thanks to the operational features and the reduced amount of maintenance that you need to perform, you can also save on your OpEx costs. The main feature that AWS Greengrass provides is the ability to synchronize the status between the cloud and the device. This feature is called AWS IoT Shadows. AWS IoT Shadows are documents, JSON documents, which represents the status of the device. Those documents are managed by AWS and are hosted on the cloud. In order to synchronize the status of the device, the cloud automatically reached out to the device, understanding which is the document status at the edge, synchronizing it with ones on the cloud. This happens also if you change the status from the cloud, which means that every change that happens on the cloud also is propagated asynchronously to the edge. Asynchronously because this can also happen on unreliable connectivity, which implies that if you change any status of a device from the cloud, this status is then asynchronously synchronized with the device itself as soon as the device comes back online. The logic at the device can be managed using a Greengrass component, which out of the box helps synchronize those documents with the AWS cloud. The custom logic then to perform the action on top of a status change can then be implemented using custom logic in a component, as we are going to showcase in our demo shortly. This is the detailed demo architecture. So we have our components that we just described, but we also have a detailed diagram of what we are installing. In this case, we have our Greengrass, which is installed in an EC2 instance. And also here we have a simulator, which is in this case a Modbus simulator, simulating a DER, which can be controlled through Modbus, for example, a switch or a boiler. There are a number of components within this installation of Greengrass. These components are directly managed from the cloud by AWS Greengrass. So there is a deployment here in Greengrass saying which are the components that are deployed in our device. So I can directly change or manage, update or remove all the components directly from the cloud, and Greengrass is responsible to propagate those changes at the edge. The components which are provided out of the box in this case are Shadow Manager, which is responsible to update and keep in sync the shadow which is in the cloud with a shadow which is at the edge. So the Shadow Manager will keep a shadow here and is responsible to keep that synchronized. The Shadow Manager for each shadow change will send a message to the broker, to the main component, which is an internal broker here at the edge in Greengrass. Another out-of-the-box component is Modbus TCP. This Modbus TCP component is responsible to convert messages coming from the internal broker in MQTT towards Modbus. Finally, the third provided component is the Log Manager. Log Manager is a component which is responsible to send messages and logs directly to CloudWatch for all the components. So all the components are logging locally, but Log Manager is sending the logs to CloudWatch. So we don't need to access the device to read the logs. Nucleus is the main component, and it's the runtime of Greengrass, which also hosts the broker, the internal MQTT broker. Modbus Controller, it's the only component which is custom. Currently, Modbus Controller is reading messages from the MQTT of the Shadow Manager. This is meant to read every change of the status coming from the Cloud Shadow. Every change that is read from the internal MQTT is then converted to a Modbus TCP command, which then triggers the change. Clearly, this also works backwards. From the Modbus confirmation, the change should go up to the shadow and back to the cloud. But let's see this in a more detailed diagram. Here we have a simple application on the left in our sequence diagram, which is triggering the change towards the IoT core, triggering a shadow update. Shadows have two different status. One is called reported and the other one is called desired. Within the shadow, we find both, but we operate on one or the other. If we want to change the status of a shadow, we operate on the desired. If we want to change the reported, so the actual status of the device, we operate on the reported. So since we want to change the status of the industrial DER, in this case, let's say a boiler, we change the desired state, sending a shadow update saying, please set the status to false. The IoT core then is responsible to propagate this change to the edge device, so Greengrass, setting again the status to false to the internal shadow of the device. Our custom component then will convert the message which is coming from the shadow to the Modbus command using the Modbus TCP component, which is triggering the turning off of the device and an eventual echo response from Modbus. This echo response implies that we can confirm to the shadow that the change has happened. So the update now is from the device to the cloud, saying the shadow update is now reported to be false. So it's actually turned off. And this shadow update happens also towards the application, confirming that his first request of updating the status device is done. And now the reported state is false. Here we have our demo running in live. Here we have our device. Let's see the device. So I go to AWS IoT and I go to all devices and things. And finally, I click on my device, which is the IoT DER dev derms gateway. And this device has a shadow, as we said. And current shadow is that the compressor, in this case it's a compressor, its status is true, which means that it's turned on. If I go to CloudWatch, I can see that I have already reporting my messages of logs for the Modbus controller and the Modbus TCP. The Modbus TCP is reporting that the connection is established, meaning that it's actually connected to the Modbus TCP component of Greengrass is actually connected to the Modbus simulator, which is on the other end on the EC2. Here we have our gateway waiting for the shadow to change. And specifically the Modbus controller, which is listening to the shadow changes and is just waiting for the shadow to change. In order to change the shadow, we can operate using MQTT or eventually also REST APIs, or we can also change this shadow document directly here from the console. So what I do, I just go here and change the desired state to false and update. Once this status is set to false, the reported status immediately goes to false. But let's see what happened. So here we will see that a number of messages have been processed. Let's see what happened. So first of all, a message is being received retrieving false from the status. Then, of course, because we changed it to false. So what the Modbus controller is doing after he's received the false from the status change is sending the command to turn off the thing directly to the broker, which then send the message to the Modbus TCP component. Because it's listening to the broker from that channel. So the Modbus TCP received the message and then directly send it to the Modbus simulator. The Modbus simulator then returns back the message to the Modbus TCP, which publishes a message to the broker, and we can see that this is the answer that we have received from Modbus, which is write single coil and setting off to value 1. So the thing is off. So now the Modbus controller is saying, okay, I finally received the confirmation, so I'm successfully publishing the reported compressor status false back to the cloud, which then immediately change the compressor status of the reported to false. So to recap, you can use AWS IoT and AWS IoT Greengrass to control DR at scale. All the AWS IoT cloud offerings are fully managed, so you don't need to worry about scaling or managing servers. Remember that this is just scratching the surface. There are many more features out of AWS IoT and AWS IoT Greengrass that we could not have the time to cover. So I really encourage you to dive deeper and reach out to understand more, which are the more features that you can leverage in your AWS IoT or Greengrass and Edge applications. And remember, use AWS IoT technology to also innovate more. AWS IoT Greengrass also supports superior IML integration. You can deploy SageMaker models or your own AML models directly to AWS Greengrass with models that you have trained directly in the cloud. This is just an example, but there are many other features that I would love to talk about. So please reach out anytime, and I hope this presentation was interesting to you. Feel free to send across any feedback. You can find my contacts below. Thank you.